The aim of the experiment is to demonstrate two approaches to prevent resonance, one of which is to shift natural frequency of the system, and the other one is adding a vibration absorber to the system. A spring mass damper system shown in the figure represents a physical model of a machine supported by a flexible base, like amortisers, elastic rubbers, unrigid base itself and so on. Here, m is the mass of the machine, K and C denote the equivalent spring constant, and damping coefficient of the base, respectively. Ft is the exciting force field created by centrifugal effects of unbalanced rotating shafts, and other moving unbalanced components of the machine, especially at high speeds. Simple behavior of this repeated exciting force can be represented by this harmonic function given here. Notice that this exciting force can be created by an unbalanced mass, m' with unbalanced distance, r at constant angular velocity, omega of the shaft, since centrifugal force become, F0 equals to m' multiplied by r and omega squared. This exciting force causes vibrations on the system, and normalized shaking force, T, transmitted to the base. On the other hand, natural frequency, omega n, of this system is known as tendency of oscillations with amplitudes without exciting force after an initial disturbance. Maximum amplitudes occur when the frequency of the exciting force, omega, matches or approaches to the natural frequency, omega n. This phenomena is called resonance, that occurs at omega equals to omega n, where the system undergoes dangerously large oscillations. If the angular velocity of the motor is required to be close to the natural frequency, then resonance phenomena has to be prevented using various methods, two of which will be demonstrated in this experiment. The system in the figure is a single degree of vibrating system such that its position can be precisely defined by a single independent parameter. X normalized amplitudes of a single degree of system is shown in the figure, where delta St is static deflection of the spring under the weight of mass. Here, X denotes amplitudes of vibration. Horizontal axis, omega, divided by omega n, is the ratio of angular velocity, omega, of exciting effects to the natural frequency of the system, omega n. E2 is the damping factor of this equivalent spring effect. When an absorber is added to the system, the whole system will have 2 degrees of freedom. One is the deflection of the actual mass of the motor. The other one is the deflection of absorber mass. When the natural frequency of the absorber is properly adjusted, the system comes to rest at resonance frequency. Instead, the absorber comes to resonance. This is because the system now has 2 natural frequencies as shown in the figure. We are going to use the following equipments for this experiment: a beam, a DC motor, a spring set, a motion detector, a data acquisition device, hangers and bunch of different masses, a power supply, cables,